Okay, we're sitting here with Thorsten Schumm from the Technical University of Vienna. He, for several years actually, was involved with a project called nuClock. Now, the name already suggests what the project was about, and it was a FET project. So we know it's certainly about both longer-term research and technology. But Mr. Schumm, please tell us a little bit about the project. What were the aims, what were the specific research challenges and the long-term technology goal?
Okay, so the nuClock project is about building a new type of clock, which is a nuclear clock. You see, it's a game of words. A nuclear clock is a new type of clock. It is different from the existing atomic clocks as they are used in GPS navigation systems, for example. And the aim is to build a clock which is more robust and more precise, so it can be used, for example, in space applications and also for autonomous vehicles and stuff like that. So for that, we try to manipulate an atomic nucleus and use an atomic nucleus of a very specific isotope as a clock source, as a ticking device, essentially to pilot this nuclear clock.
All right, you mentioned a little bit about the longer term technological objectives. So how far did you get within the project, or what's the application areas that this clock would open in general?
So this is basic science essentially. So it's at the very starting point. When we started this project, it wasn't even known if this nuclear specific state that we want to use for this clock actually exists. There was a controversy in the literature, and it was one of the games of this project to actually demonstrate that it exists and can be exploited for this kind of clock. So we were successful in this. We didn't build the clock, but we laid the groundwork, so let's say the clock work to some extent. So this clock works on lasers, so that means essentially we need a laser to manipulate this nuclear resonance or this nuclear ticking device. And these lasers didn't exist at the beginning of nuClock. So we joined forces with a laser company and developed a laser system that we can use for this application. But it's now a commercial product, so it's being used for many other applications that we actually didn't even think of in the beginning of this project.
Right. Tell us a little bit more about the project itself, about the partnership, and maybe the setting.
Mm-hmm. So it's actually a very large consortium. So we have 8 partners. Formally it's 7 because 2 of them are Max Planck Society. So there are 2 different institutes of the Max Planck Society. But these partners, they joined forces on this project, and several of them did not know about the possibility of a nuclear clock in the beginning. So some of them were actually there to bring in specific technologies or methods that we need for this kind of research, where these partners were experts in, and they hadn't even heard about the possibility to work on a nuclear clock. So the laser company didn't know about it, and we had several other partners that provided specific techniques, detector techniques, excitation techniques, radiochemistry, and specific expertise that we needed for this project that we kind of pulled together to make this project happen.
How happy were you with the project's outputs, maybe both in terms of scientific output and technological output?
I think we were very happy and very successful. So as I said in the beginning, it wasn't clear whether the general approach is valid or whether it can lead to a viable technology in the long run. And we are now certain that this can work, and we actually continue to work on this in another EU project. So in that respect, I think we were very successful. And I think the second aspect is that we, along the way, produced a lot of techniques and technology, as I said, is now being used for other purposes in very broad ranges, including medical science. And again, that's something we didn't anticipate. But once you build a device or a technology that nobody has, or that has capabilities that weren't there before, other people jump on that and say, oh my God, I can use this for a completely different application.
in fact, you not only produced technology, you even produced art. Maybe you want to elaborate a bit on how this happened and what it was that you did.
Right, at the very beginning of the FET project, we were joined with an embedded artists in the framework of a project scheme that was called FEAT, Future Emerging Arts and Technology. And there was a partnership with Kerstin Ergensinger from Berlin, who is a figurative artist who does mainly installations, quite tech-based installations, in fact. And so the fact that she's married to a physicist also helps in developing a common language quite rapidly. And she followed this project throughout the full duration until the end, and produced several artworks in the topical field of the nuClock project. So nuClock is something that has to find out a signal within a large noisy environment. So there's a lot of noise. You can even think about acoustical noise, and there's a very tiny signal we have to isolate. And this concept of noise and information is something that Kerstin worked on and produced several installations, which were actually shown even in my institute.
Yes, tell us a little bit more about this. Our experience from the FEED project was that the creation of a physical piece of an artwork is very different from the way of just, let's say, writing paper or giving a talk, because these things, they create an emotional reaction and they are carried from one exhibition to the next. So in a sense, the artistic piece will be around for quite some time. So how do you relate to this, let's say, to this part of science communication? Do you think this was useful, or even for yourself, did it create interesting discussions?
I think it's way beyond useful. I think it's absolutely mandatory that we find ways to put a spotlight on what we do from all possible perspectives. And this has something to do with researchers taking responsibility for what they do, because it may strongly impact on society. So a little bit of reflection is in place. But also I think there's a playful act to it, or a playful component where you don't take yourself too serious, but take a step back and see what are the underlying principles that you are working on, and where else do they appear. The question of noise and the perception of signal is something that we experience in day-to-day life, and children learn that without ever being taught. And so it's something that I think it's just enriching to broaden the perspective and to put our day-to-day activity also to a challenge, and try to explain this and illustrate it in all kinds of different ways.
Right. Now FET or nuClock was a part of the Future and Emerging Technologies program, which has very specific characteristics. It tries to be both a leading edge research program, but it has a technological objective. Maybe can you comment on how you experience this combination of basic research plus technological aim a little bit?
I think this is often perceived as contradictory directions, but I think this is a misconception. I think, at least in my field of experimental physics, whenever we create a new device, a new technology, a new skill or method, this allows new investigations. So in our case, the development of machinery, of lasers, of detectors, spectrometers, and so on, goes hand in hand with the scientific advancement. And so this is why in this consortium we had like physics groups, but also we had a technological core group which were working together. So I think this can be a fruitful combination. And as I said, there were several unexpected technological offsprings that wouldn't have been there if it were not triggered by a fundamental research question.
Do you think programs like FET are important, and should they be maintained?
Absolutely. So I think what was good about the FET project is that it forced the researchers to think about what could be done with the devices and the technologies they develop beyond the specific goal of what they do. And in our project, we had a technology transfer officer or somebody who helped us to think about what we have developed in other contexts. And that in the beginning, that was let's say a little bit out of our comfort zone, but it really helped us to identify which technological achievement we have actually done and what the value of the nuClock project actually was beyond the specific goal of the nuclear clock.
Great. Maybe tell us a little bit about what happened since nuClock is finished now. But what are the insights or the research directions that it opened, or how is it to be continued?
So first of all, we have the great possibility to continue the research on the nuclear clock now in the framework of an ERC synergy grant. So several of the initial partners of the FET project are now continuing along this direction. There were some technological adjustments, so something we learned along the way. For something we don't need specific technologies anymore, we bring in new ones. But one of the offsprings, for example, is that we had to do very specific chemistry for the nuClock project. So we were building a chemistry cluster at the Vienna University of Technology, which is now a standalone service unit. So it's essentially a small company that provides chemistry services in a specific topical area to other customers or research groups. So that's another something that developed out of this project and now lives its own life.
It is my experience as well that sometimes in these projects you get completely new lines in the development that you just would have never predicted. And do you think the commission programs are generally flexible enough for these directions?
I had the feeling, yes. So we were nicely followed, accompanied, and supported by the project officer, but also his team and the reviewers. And I had the feeling that there was a genuine interest in openness, in flexibility. I mean, these are long-term projects. Within 5 years, there are new information that come in from the side. You have new findings. You have to readjust continuously where the project is leading. And I felt we had this flexibility.
Right. I don't know how much you know about it, but the FET program has come to an end, and it's going to be moved to the EIC Pathfinder as a part of that larger initiative. If you think about it, what would you hope for the future of the FET program? Which are the features that you think should be maintained, and maybe which other aspects could be improved?
I think it's important to keep the basic research aspect as a starting point for technology development. I think a great physics questions like the task to find the origin of dark matter or questions around the Big Bang, they seem extremely abstract, but to answer and tackle them, you have to build state-of-the-art technology, which is a very concrete, very substantial thing that happens in the lab. And we build detectors, which, as I said, are now used in medical physics and in pharmacies to some extent. And so there's often this feeling of conflict between fundamental research and applied technology. But I think these projects go hand in hand. And I think the strength of FET was to filter out these projects which have the potential for both. And I think this should be maintained.
Many thanks.